so now what I'm going to do is I'm going to look at proving this. Let us think of a line charge. And first what I'll do is I will first prove that the answer for the line is the same as the answer for the arc. Then I'll separately prove that the answer for the arc is equal to this. So that way we have two things done. We know the answer for the arc and we know the answer for the line. Okay. Now this is not the way I came up with this thing. Okay, because what I did was a much more longer complex mess. But it's easier always, once you know the answer, to work back and see why it works. Okay, so let us take this. So if I now want the field here, the field is the sum of all the fields caused by every single element. Okay, so let us first construct like we did here. Let me just construct. First, let's take this length and let us draw. So these lines don't exist. This also doesn't exist. Actually, I'm just going to construct a arc with this as the radius. Okay. What I'm going to do is to show you that if I took some random element here, the field because of this guy there is the same as the field of that corresponding element here. And if I show that, then if I add up every single field for this and for this, you will see that it is the same. So let me again restate what I'm saying. I'm saying that this guy's field, so this is a random element. Now this guy's field here basically is going to be some answer in this direction. Correct? Now if you look at this little thing here, now this will also cause a field there. What will be the direction of the field? Same, because it's both the same line. Now this field is in that direction. Now first of all, I'm going to claim that that green line and the black line, they're both the same. That is the field caused by this fellow there, this fellow's field at P. Let's call this point P. Okay, so this guy's field at P is equal to this guy's field at P. So let me call this A and let me call this B. A's field at P is equal to B's field at P. Field at P due to A equals field at P due to B. I don't have to prove that the directions are equal. That you know, because of the way I have constructed it. It's after all just a line. All I have to prove is the magnitudes are equal. If I show you the magnitudes are equal, I'm done with this. Now that doesn't necessarily mean that this entire thing's addition and that fellow's addition is equal. I will show it to you now, because if I took another point here, let's call this A dash, then I could always draw a line like this. So that means I will get this, and that means I'm going to get another point there. I'll get a B dash. Right? Now, if this was true, this is A dash, A and B are random points. So A dash and B dash are also equally random points. So if it's true for A and B, it is true for A dash and B dash. For every such point A, there is a corresponding point B once, only once. It's unique, right? If I start here, there is a point there. So when you start with this point on the line, you have a corresponding point on the arc. You come here, there is a point on the arc. You come here, there is a point on the arc. Point on the arc, point on the arc, point on the arc, point on the arc, and so on. So for every point on the line, I have a corresponding point on the arc. Now, if I say that for each of the points on the line, the field is the same as the point for the arc, if I add up all of these fields, it must be true there. Think of it this way. I have 10 vectors. I have two different sets of 10 vectors. For vector 1, I have vector 1. Vector 2, vector 2. Vector 3, vector 3. If I add up these 10 and add up those 10, you must obviously get the same answer, because individually they are equal. Point by point, they are equal. Now, let me tell you something interesting here. This charge is not equal to that charge. This guy's distance is not equal to that guy's distance. I am not saying that these charges are equal. In fact, the length of what I am going to take here, the small element, the size of that element, and the size of this element will be different. It has to be. Only then the charges would be different. The elements are different, their sizes are different, the charges are different, the distances are different, but the fields are the same. Why? Let us look at that. So now let us think of how do we prove this. So what I'm going to do is to take this element. So I want this element. First of all, I need to refer to that point. Where is this place? You can say, well, it is x away from this perpendicular or x away from that end. Actually, instead of doing all that, what I'm going to do is I'm going to say this angle is phi. So how far away is it? Where is that point? Draw an angle phi from the perpendicular, extend it, wherever it meets, that is the answer, right? Now, but that doesn't tell you the element, that only tells you the starting location. Now I want to know what is this length. Okay, well, this length would be a differential element. How much is it? Now let me do one thing. Let me draw a smaller piece like that. So that I have a small change in the angle, because if I have assumed the angle to refer to that place, see, in all integration, the key point is to first find out where are you talking about, where is the location of the element. And once you know the location of the element, then you can look at the differential element. So the location of the element, now I am using phi to refer to the location. Now phi also tells me the location of this point, this piece, right? Now this is d phi. That is going to tell me when I change my like when I change this angle, this increase in the angle is d phi. Now what about this b? At b, what is that extra piece? What is that element that has been created? Well, this is r, and so what about that? It's an arc. So that is also r. So what about this length that I have got? It would be r into d phi. You know that for an arc, if this is r and this angle was theta, this would be r theta, right? Now this is a differential angle, that's all. It's a small angle. So in fact, for that it should obviously work, because it works for any angle. So what is this length? It is r d phi. What do you think about this length? First of all, you can't call it this radius into d phi, because that would be this arc length. That is not correct. So how do I find out what is this length that has been created by moving this angle phi? Because that is where the correspondence comes in. Every point here has been counted there. So the correspondence comes in only if I take this length. How do I find that length? Let us think. If this is r and that is phi, what about this? This divided by r, if I call this x, x by r, what is that? Tan phi. So if x by r is tan phi, what is x? R tan phi. So this length is r tan phi. Actually, it is an arrow from here to there of length r tan phi. So what about that increase that I'm going to get? D of r tan phi. So this thing is d of r tan phi. R is a constant, so I can pull that out. What is d of tan phi? What is the differentiation of tan theta? Secant square theta d theta. D of tan phi is secant square phi d phi. Well, if I want a differential, if I want just differentiation, then you divide it by the d phi. We don't want a differentiation done here. We only want a differential element, and so that is secant square phi d phi. So that tells you how much length I have. The lambda is the same for this and for that. So the charge here, how much would the charge be? Lambda times this. So let me put that here and say that lambda times this is dqb. Okay? And what about the charge here? Lambda times this differential element. So it will be lambda times d of r tan theta, or r tan phi, sorry. So it would be lambda times d of r tan phi, or lambda r secant square phi d phi, and this would be dq at A. The charge here is this much and the charge there is that much. Now the field at P, I want these two fields, right? What is the field at P because of B? Let us try to calculate. So field at P because of B is kqb, the k charge, k times charge, by this distance square. So let me write it as it is, k qb, which is lambda r d phi, by this distance square. What is that distance? R. So it is r square. So you see, this guy had no sine theta, cos theta, nothing, cos phi, nothing there. It is nicely just proportional to d phi. You expect that because this arc length is proportional to d phi, and therefore the charge is proportional to d phi, and therefore you expect the field to be proportional to d phi. Now the question is, what is the field at P due to A? What is A? That is A. Now clearly the charge is very different. So I have KQ. What Q? This Q. But this Q is lambda r secant square phi d phi. Now I've got a secant square phi here. It's a little messy. But hold on, we still haven't finished. Divided by, what distance square should I divide it by? This distance. Right? Because you are looking at this charge is this far away. This charge was actually closer. It was just distance r. This charge is at this distance. What is that distance? If I call that distance as the hypotenuse of this triangle, it is the hypotenuse, h. R by h would be cos phi. So what is that length? R by h is cos phi. So what is that length? H. R by cos phi. But what is cos phi? R by cos phi is r secant phi. So this length that we are talking about is r secant phi. So that means here when I do the square of it, I should get r square secant phi square. And we had a secant square phi at the top, but we have a secant square phi at the bottom, and they beautifully cancel. And so you are left with k lambda r by r square, k lambda r by r square, d phi proved. Okay, what have we proved? We have proved that the field of this guy there is equal to the field of this guy there. So we have proved this statement. Okay, now why is this true? Think about it. It just turns out to be nicely, magically true because this point has a different charge, this point has a different charge, this has a different distance, that has a different distance, but the charge by the distance square turns out to be equal. Okay, so it just happens to be equal, which makes our life so much simpler. Now since this cancels out nicely, what I have proved now is that the field of this, because if I took any point here, basically I have to take a little longer length. I'm not taking the same length because if I now took that projection like that, if I took this and I took that, you can see that I'm taking a smaller piece there, I'm taking a larger piece, but this larger piece is at a larger distance and it beautifully cancels out. So the field of this guy there and the field of this fellow there is exactly the same. What I have not yet proved is that it is equal to this when I integrate. Now I don't need to do the integral for this, I will do the integral for the arc. But the integral for the arc is so much simpler, so therefore let us do that and finally conclude that this is true. And once you know this is true, you can now use it across wherever you have a finite line charge. So please remember the formula because it's lambda by 2 pi epsilon naught r. Anyway, this piece you need to remember. So you just have to have one additional piece which is sine theta by 2. Okay, now let us prove that for an arc the answer is this. Okay, once we have done that, we have completed our proof. So now let us look at the proof for the arc. Okay, now instead of making the arc look like this messy thing, what I'm going to do is I'm going to take the arc and make it symmetric. It doesn't really matter because if the arc looked like this, just turn this board around, then you have got the answer. For an arc, it doesn't really matter, right? Now, for a line, it does matter because it's not symmetric. Okay, for an arc, it doesn't matter because you can prove it anywhere. For the line, if you just prove it at the midpoint, it doesn't mean that you have proved it for the edges. And for arc, remember, we are only proving it for the center. Whereas for the line, we have proved it for any place because for any place you can draw an arc. Whereas for an arc, you can't convert it back into something else. So let us therefore prove it for the center for an arc that looks nice and symmetric about the vertical axis. So I have here a vertical line and it is equal on both sides. And so what we are going to do is to say that this angle was, the total angle is theta. Now, if I took a differential element, that is I took a small element and I want the field due to this small element that would point in that direction, this is of radius r, and if I call this angle theta, or let's make this angle phi actually, because we are going to use theta for that. So if this angle is phi, then this small element here, this I should have extended it around like this. That means there is a differential angle d phi, and this length here would be r d phi. We have just done all this, so you know it. And it has a linear charge density lambda. So that means the charge would be lambda times this length, and so that is lambda r d phi. And the field is kq by r square. So it is k this, which is lambda r d phi by r square. Luckily for us here r is constant. Except this field is pointing like that. You know that the final answer to this is going to look like that. Why? Because the component of the field in this direction, which actually is going to be a smaller component, that is going to be this size, right? Is going to be this field cos of this angle. And then there is going to be a component in this direction which will cancel with a corresponding guy here. Because this fellow's field will be like that. This will have a component like this, and it will have a vertical component. The vertical component for this one and the vertical component for this one will both add. So all I need is to take the vertical components, because the horizontal components will all cancel. Okay, now if I want the vertical component, what do I need? I need to know this angle. But I already know this angle, because the angle of this line with the vertical phi, this is the extension of that line, this is the extension of this line, so this angle is phi. So what is the component? If this was E, let's call this DE, small element, right? This fellow's DQ's, this is a DQ. DQ's field at that point is DE. Now DE cos phi would be that element, right? So if I want the vertical component, I want DE cos phi. That's the only thing I need. And I need to integrate it all the way from here to there and double it. So either I can write this as an integral from this phi to that phi, and phi was pointing in that direction. How do I know that? Because d phi was pointing in that direction. So if you wanted to start phi off there, and this is the direction we have taken for phi, where did you start? You started at minus theta, because this angle is theta, you started at minus theta. So you have to integrate it from minus theta to plus theta. So phi goes from minus theta to plus theta. This would be the answer. Now this I want to find out. Let us write this down carefully. What is DE? We already know what is DE. So let us expand that out. R cancels out. One R cancels out. So we are left with k lambda by r d phi. Cos phi d phi, because into cos phi. So cos phi d phi. I need to integrate this from minus theta to plus theta. That is, phi goes from minus theta to plus theta. What is cos phi d phi integral? Sin phi. Because differentiate sin phi, you get cos phi. So this is going to become sin phi. So it is k lambda by r sin phi between the limits of minus theta to theta. And so this is sin theta minus of minus sin theta. So this is going to be k lambda by r into sin theta minus sin of minus theta, which will basically become plus sin theta again. So I've got 2k lambda by r sin of theta. But in this whole thing, the whole angle was 2 theta. So right now I have derived it for 2 theta. If I want it for theta, the whole angle was theta, then I should substitute here theta by 2. Now let us actually look at this and explain what this means. This k is 1 by 4 pi epsilon naught. So if I substitute for that, 2 times 1 by 4 pi epsilon naught becomes 1 by 2 pi epsilon naught. In fact, that's why you get this 2 pi epsilon naught. You have a lambda at the numerator, so it is lambda by 2 pi epsilon naught. That is the 2k. So the 2k lambda looks like this. Then you have the r, so that comes in here. And then you have the sin theta, which I'm going to write it as sin theta now. But you have to keep this in mind that I derived this for a total angle of 2 theta. Okay? If I want for, look at this, here this is theta. I like this formula better instead of worrying about this, because you assume that the angle is theta, then the answer is sine theta by 2. Just keep that in mind. It is sine theta by 2. So what we have done is for an angle of 2 theta, but it's exactly the same, because now if I have an arc of angle theta, the answer is first of all going to point right in the middle of this, right? That is symmetric, and the answer is going to be lambda by 2 pi epsilon naught r sine of theta by 2. This is theta. Don't get confused by the fact that this was sine theta, because there the whole angle was 2 theta. So I hope this is simple and clear. We have now proved the answer for an arc. We have also proved that the answer for the arc is the same as the answer for the line. So now any combination of lines, you should be able to convert them into arc and find the answer. And you can, in fact, you don't even have to convert, you can just remember it like this, that it actually happens to be at the angle bisector line. The electric field is along the angle bisector. So that is an important property that probably will be useful in many different types of questions. Is that clear to everybody?